everyone to the 6th RRI Statistical Physics School. So, how many people are there from the previous year? Okay, so many of you have already heard this talk probably, and some of it will be repeat, but it's good to hear, I guess, the same thing couple of times. So, okay, my name is Abhishek and this is Sanjeev. Okay, so I guess there's not any other information, right? Okay, so we just start this lecture. So, what me and Sanjeev will do is basically we will talk about some very elementary things which will get you kind of oriented for the lectures in the next 2 weeks. Okay, so I will mostly talk about random walks, and Sanjeev will talk about Brownian motion. So, random walks is basically the discrete version, and so roughly speaking random walk is the discrete version, and Brownian motion is the continuous version of the same thing. Okay, so I think all of you probably have already heard about done some at least taken some course where you have heard about random walks and all. So, let me start with giving a brief history of where this random walk problem started. Okay, so this term random walk was first I think coined in a paper in 1905 by this person called okay, so this so there is a paper in Nature 1905. Okay, and in this paper he basically describes a model for understanding how if you have if you are in a forest and like say or in a city and you have a bunch of mosquitoes which are in a given region, how does this population of mosquitoes spread in time? Okay. So, that is the question he asked, and he said that what typically mosquitoes do is they do a random walk. Okay. So, they move some distance, let us say some distance A, and then they change the direction randomly, move another direction A, distance A, and keep doing this. Okay. So, they keep taking steps of a fixed size, but in a random direction. Okay. And so in this collection of n mosquitoes, so you start from some n mosquitoes in this region, and each of these guys is doing basically that is what a random walk is, and you want to know how this the size of this, for example, size of this population grows with time. Okay. So, this person basically asked this question in this so he proposed this model for understanding how population of mosquitoes evolve, and he posed this as a problem. How do you solve this problem? Okay. So, in a subsequent edition of this volume, there was a paper by Rayleigh where he actually solved this problem. Okay. So, this question was posed by this person, and Rayleigh basically solved the problem, and he showed how it should spread and so on. So, what Rayleigh was he had independently been looking at something like a question of like if you have waves traveling in some random medium, how do they propagate? Okay. So, normally you know that if you have waves with two phases which interfere, then they can either be constructive or destructive, right. So, if you have two phases e to the power I theta 1 and e to the power I theta 2, then depending on the phase difference you can either have constructive interference or destructive interference, and the amplitude, if each of these amplitudes is A, the full amplitude can be either 4A square or it can be 0, right. So, you can have either. So, he asks if you have like n random waves, then what is the net intensity. Okay. So, that is like you will see that that is actually equivalent to this mosquito problem. Okay. So, just sum of n random complex numbers is also basically the question you are looking at here. Okay. So, these are two completely different problems, but they are described by the same mathematics. So this is random walks, and Brownian motion actually was first studied by this person called okay. So this was and what this person was studying is he was trying to build up a model okay. So this was actually in 1900. And so in this context, he was basically looking at things like prices of stocks. Okay, so it's quite surprising that even in 1900, he had enough data on stock prices, and he was trying to sort of understand this data mathematically. And he thought that just if you model the prices as like a Brownian motion, then you can understand. Then you can develop some sort of understanding. Okay, so. Okay, so he actually developed a lot of the theory of Brownian motion like before. So afterwards, of course, it was the mathematical theory was given by Wiener, but a lot of his results were actually derived in this in this work. Okay. Okay, so around the same time, I mean, which you all probably know, Einstein was trying to understand. Around so in 1905 he wrote a paper on Brownian motion, and so basically he was trying to understand the motion of so if you have a fluid and you have a colloidal particle. So this is a particle which is like 1 micron big, okay, much bigger than the particles in the fluid. And so if you look at how this colloidal particle moves, you will find that it moves in a random way, right. So I mean, so just to understand this motion of this big particle in a sea of small particles, I mean Einstein developed this theory of Brownian motion. So okay, so this is modeling. Okay, so right, yeah. So I mean, of course, this problem you might try to understand just from purely a Hamiltonian. I mean, this is a completely Hamiltonian system. So if you try to understand it from complete microscopic, this is very hard, right? So I mean, so this is basically a simpler model, which through which you can understand many things. Okay, and so using this theory, actually, it was one of the first. I mean, some of the predictions that he made from this Brownian motion model led to the first verification of the fact that actually fluids have atoms. Okay, so this and then there was this experiment by Pera, where he actually just looked at the trajectory of this kind of particles. Okay, so he just looked at under the microscope and saw how this and just looked at the position of a colloidal particle after every, let's say 10 seconds or something. Okay, and he plotted the track, and then he found how far it has gone in some time t. From that he estimated the diffusion constant, and from that he could actually, this was one of the first accurate so afterwards I think Sanjeev will discuss this. I mean, just looking at this Brownian motion, you can actually estimate the Avogadro's number. Okay, so this was one of the first accurate determination of this constant, the Avogadro's number. Okay, which also established, and this experiment kind of established the sort of microscopic, I mean the atomic nature of matter. Okay, so so we see that random walks have been studied in various contexts. I mean, just trying to understand movement of mosquitoes or like random waves, and in this case financial time series, and in this case something more physical like colloidal particle in a fluid. Okay, So this I think, so we have a microscope at some point, maybe in the tutorial we will try to show you like how to see this. Okay. So how many of you actually have seen a Brownian motion under the microscope? No one, is it? Okay, so this is something really nice. Okay, I mean you should just imagine, like you take a beaker and you put some water, right? I mean there's absolutely, and it's completely closed. Okay, and you have a colloidal particle, and then you see that it just keeps moving randomly. Okay, so it's a really fascinating thing. Like, I mean, where does it get energy from? Okay, so it's of course getting energy from, I mean, so that's what Brown saw, and he was very surprised. I mean, so first he thought that maybe these are living objects. He was looking at pollen grains, so he thought it was living objects, and then he tried various ways to actually make sure that they are dead. Okay, and then he tried various I mean, like he had I mean hundreds, like a 100-page thesis just trying to understand this simple observation. Okay, so just to you have to make sure that there is no like convection and air currents and so on, just to make sure that, I mean, why are these guys moving at all, right? I mean, just to eliminate all other sources, and the fact that it just comes from the microscopic nature of the fluid, that is quite a remarkable thing. Okay, so it's so we'll try to set up an experiment here in the tutorial where you can actually see like Brownian motion. Okay, so it's very simple to do it actually, even if you have a very simple 1000 rupees microscope, and you just take milk in water and put it under a slide and do take some care to seal it properly and so on, you can just see it quite easily. Okay, so so is there any other place where you have seen this sort of Brownian motion? Huh? No, where you have seen, and you just said you haven't seen Brownian motion in, but have you seen pollen grains? I mean, put it in water and, huh? No, how did you see it? How did you see it in a microscope? Okay, but that's what I asked just now. Okay, so you have seen Brownian motion under a microscope. So what did you do? You took pollen.
Yeah, some flower, pollen grains of flowers, took it and suspended in water.
Okay, right, yeah. But is okay. So that's is there any other place where you have seen Brownian motion or diffusion? Okay, right, yeah. So if you spray deodorant in a room, that somehow reaches far off. Okay, like it. Okay, so is that is that Brownian motion? Okay, so actually that's not Brownian motion. It's diffusion, but it's not Brownian motion. Okay, so the and the reason that like if you spray deodorant, it reaches you. If you so you can calculate, so from the theory that will teach you, what you will find is that there is something called a diffusion constant, and this for a Brownian motion, this is basically given by a formula like this. Okay. Okay, so this is a so this theory of Einstein basically tells you that the diffusion constant, it depends on the temperature of the fluid, the viscosity of the fluid, and the size, the radius of the Brownian particle. Okay. So if you use this formula for deodorant, you will find that the diffusion constant is really small. Okay, and the time it takes to reach from here to there will be like maybe 1 year. Okay, so it's not really Brownian motion. It's diffusion. If you really think of they are moving randomly. Okay, so what do you think could be the reason that it actually reaches you? Can anyone make a guess? I mean, it's not the diffusion in the way of like Brownian motion, but it's still somehow it's not moving straight, right? It's doing some random motion. But what is the source of the random motion? Huh? Turbulence in there, right? Yeah. So typically in this room, I mean, you will have like all sorts of temperature gradients, right? I mean, like the temperature of most of you is higher than some place here, and there are air currents, and also there is air from the windows and so on. So even if you seal the room, you will find that there are air currents all the while. Okay, so it's just convection, and convection is also kind of random. Okay, so it's still diffusion, but it's not Brownian motion. Okay. So there you will find that diffusion constant is much larger, and to calculate that is it doesn't depend in this way. It's a different thing. So similarly, mosquitoes of course is not given by this theory. I mean, they are also diffusing objects, but it's a different thing. Okay. Another example is if you just take some beaker of water and put a small amount of ink, is that diffusion? And you will find that the blob slowly spreads, right? Is that diffusion? I mean, how long does it take to spread the whole volume? Is that diffusion first of all? It's probably yeah, it's diffusion definitely. I mean, if you actually do the experiment, you will find it takes a really long time to actually, if you don't disturb it, it takes a very long time to spread over the whole thing. Okay, actually, I think I mean, it takes a few days, right? I think if you really isolate it, and you have a big beaker and you put a drop very slowly and carefully, okay, and then make sure that it's kind of sealed, you'll find it takes a really long time to spread. Okay, so that might actually be given by this. Okay, so there are nice simple experiments you can do actually to just understand all of this. Okay, so okay, so let me just start with asking what are the interesting questions that one can ask. Supposing we are just looking at mosquitoes, and what are the interesting questions you can ask. Okay, so okay, so I mean, if you have this n mosquitoes starting from this small volume, then you'll find that each of them kind of, as I said, that's what typically happens. I mean, one of them goes like this, and second mosquito might take a different random path. Okay, so I said they are all of the same length. The distances, the step lengths are the same, but the directions are random. Okay, and let's say the mosquitoes are walking in 2 dimensions. So it's like if you look from an aircraft, you won't see their depth, right? I mean, you will just see them moving in 2 dimensions. Okay, so and what you are interested in, how they spread in the like the 2-dimensional domain. Okay, so you can just think of them as 2-dimensional walkers, and so a third mosquito might do something like it. Okay, it might go very far. Okay, so in a fixed amount of time, you find that different mosquitoes have traveled to different distances, right? So if you take a snapshot at some time t, so let's say this is the xy plane, and at some time t, you take a snapshot of where the mosquitoes are. You'll find that some mosquitoes here, some here. Okay, so so what's the maximum distance they can go? I mean, what is the maximum distance where I'll find a mosquito? 80, right? 80, because if they just keep going in the same direction, which is very unlikely, then they will reach some distance 80. Okay, so that will be actually, if you I mean, so okay, so 80 is the maximum, so that might be somewhere really far. Okay, we'll see how far that is. But now what you are interested in is like, okay, so for each mosquito you have some vector, let's say call it RI bar. So it's x. Okay, so I'll call it Rn. And you want to basically know what is the size of this cloud, right? So one estimate of the size of the cloud is given by the mean square distance of each mosquito, which is, if I have n number of mosquitoes, then this is so this is at time t. Right, so this is the average distance. Okay, so the I mean so this is this gives an estimate of how far the cloud has expanded, right? The other question one would be interested in is like if I take a ring of size r, then I want to know how many and so this is some distance dr, then I want to know how many mosquitoes are there in this small ring r2 r plus dr. Okay, so that so number of and what one would like to find is this object, okay, this distribution function. Okay, so okay, so now let's see how we go about calculating this. Uh, okay, so I just want to make a remark here. Okay, so this I'll call rho of so this is a density number of mosquitoes between R2. So this is kind of a density. Okay. So, so one point here is that here I'm thinking of the mosquitoes as kind of non-interacting. Okay, so they don't bump into each other. Okay, so then if I have n mosquitoes, then if I know the behavior of one mosquito, then it's easy to find the behavior of n mosquitoes, right? If they are non-interacting objects. Okay, so therefore here if I look at one mosquito, then what I can ask is what is the probability that it's between R2 R plus dr, right? So okay, let's just call it particle instead of mosquito. One particle. So then I can have define PR dr equals to and right, I guess this is clear. So if I look at the n mosquitoes, then this is like a density. If I integrate this, this should be 1. If I integrate this over all r, this should be 1. If I integrate this over all r, it should be the total number of mosquitoes, right? So the density and the probability are simply related. Okay. So if I just understand one guy, then basically I understand n guys. Okay. Okay, so the other point that you should remember is that which people quite often forget is this object is a PR is a probability density. So it's a density, right? It's not a probability. So it has dimension 1 over r, right? And if it's okay, so this is a and if you multiply by dr, then it's a probability. Okay, so it's PR dr is a okay. So this is just a pure number. This is something which has dimensions. So yeah, okay. And this object can be greater than 1, right? And this object will always be less than 1. Okay, so now let's do some calculations for some simple models of random walks.
First one is clear or lower?
Sorry?
The first line.
This one?
Yes.
It's probability, okay, I am multiplying by dr, right? So PR dr is the probability that a mosquito is between, this is a probability.
It's probability.
Yeah, if I multiply by dr, it's the probability.
And that P, that is row in front of the
This, which one? This one?
Yes.
This is P. If it is rho is, if I multiply by n, then I call it rho, right? Because this if I integrate over all r, it will give n, right? Because this is normalized to 1, right? I mean, so yeah, louder. Okay, so here I am defining r as the radius. No, r goes from 0 to infinity, right? So you can also define what is the, so you can also ask the question, if I take a small, let's say some small volume like this at r bar, right. So this is, let's say, theta to d, so this angle is d theta. So this is localized at r theta, and this distance is dr. So you can ask what is the number of mosquitoes in this small volume. Okay. So then you need a vector. So then you talk of so if it's 2 dimensions, you just say p x bar is the number of mosquitoes in a small volume at x bar. So so that's the so I mean that's in 2 dimensions. Okay. I mean you can either define it at a in a small volume, or you can define over the ring. If I define the density over the ring, then it's just r0 to infinity. So in this case, the normalization would be over, of course, dx and dy. And similarly, I can write it in radial coordinates. Okay. Yeah. It's just the see, I have this n mosquitoes, right? And then so initially, I mean, so there's some density of mosquitoes, right? So it's a row of I mean row of. So okay, so initially I can define a row of r bar. Okay, so at each point there's some density here, right? And that just counts the number of mosquitoes in a small volume dr bar. Okay, and then I also defined this row of r. Okay, so let's call it something else. Row maybe row tilde. Okay, and the way I define row is I just look at the, I mean, so the mosquitoes could be anywhere on this ring. Okay, so then rho r dr counts the number of mosquitoes in this ring. Okay, so this is just a density field. Okay. Yeah, so it's good to make like the simple things really clear. Okay, so if you have questions, just ask. Okay. Okay, so is this point clear, right? That it's like a difference. I mean, either I can just look at some small volume and count how many particles are there, or I can take a ring, and so there are two different objects. Okay, so now we'll start with some the simplest model of a random walk, which is just a one-dimensional random walker. So this I'm sure all of you have studied. Okay, so you have a lattice. Okay, so this is a random walk. So you have a lattice, and let's say this you number them 0, 1, -1, 2, 3. Okay, and so at okay, so now I will call it walker. I mean, it was a mosquito or a particle or a walker. Okay, so at let position of at time step n, let position of walker be x. Okay, so this is just notation. So at time, so I take so here time is also discrete. So at each time I walk, I take a step either to the left or right with equal probability. Okay, and I want to know after n steps what is my position. Okay, so I start from here. Next time step I take one step, let's say to the right. Next time step I could go either this way or this way. So then after n steps I want to know what is my position. Okay, so supposing that position is xn. Okay, so now okay, so the definition is of the model is very simple, that at the next time step it's xn plus some random number which I will call zeta n. Okay, so if I know the position at time step n, then at the next time step it's just xn plus some random variable. Okay, and what is this random variable? So it's a number which is 1 with probability half and equals to -1 with probability half, right. So, yeah. No, because okay, yeah, that's a good question. So I could, why not just write zeta, right? Because if I use zeta, that means at each time step I am using the same zeta. Okay, but each time step I am drawing a random number from a separate from this random. I have some fixed distribution, but I am at each time I am drawing a random number from that distribution. Okay, so the different steps zeta changes, right? It could be +1 at one time, next time step it could be -1. Right. So I am not using the same zeta at all time steps. So it's a function of time really, right. So that's why zeta n. Okay, and so the distribution that I am drawing zeta n is the same at each time, but the value itself could be different at different time steps, right. So that's why I need this index n. Okay, so okay, so this is basically the model. That's the definition of the model. I mean, if you like to, this is basically Newton's equation for a random particle. Okay, so if you, I mean, so normally Newton's equation is dx dt for a single particle is dx dt equal to v dv dt equal to some force, right? And if you solve this, you get x and v as a function of time. This model is this also gives you how x evolves with time, right? So this is the Newton's equation for a Brownian particle. Okay, so this is the fundamental equation. It contains all information about the process. This plus the specification of the noise. And now what we want to know is, so the first question would be, what is let's say xn. So after if I okay, so okay, so if I look at one realization, so let's say I draw time and x here. So this is n. So it starts from the origin, and let's say this is x. So what does the typical walk look like? So x versus time. So it starts from here, and then let's say I have some. So it could go like maybe first step it takes to the right, let's say, then next step also supposing it's with it might go like this, and so on. So this is one possible realization of the random walk, and so after 1 to 3 time steps it's at position 1 2 3 here, right, 5. Okay, so in another realization it could might do something like this. It might go like this, then like this. So this is 1 step, 2 step, 3 step, 4 step, 5 step. Wait, I'm doing wrong. Okay. This is x time. This is time. Okay, so I start. So this is x equal to 0, 1, minus 1, minus 2, and this is time. So time, of course, only increases. Okay, so okay, so the first step, time 1, it can go up. Time 2, it can go like this. Time 3 it can go like this, time 4 it can, so it can't go down, of course, right, because in time it can only increase. So it might, okay, so after 5 time steps it's somewhere here. Another realization could be it just goes like this. So after 5 time steps it's somewhere here. Okay, so if I do many times I'll find it on this line, it can land at various places, right. In 5 steps the maximum it can go is somewhere 5. So 1, 2, 3, 4, 5. So the maximum it can go here, or it can land here, here. I mean, so actually it can't land in all places. but at least between -5 to 5, that's the range it can go. Okay. So if I do this large number of times, I'll find that many times it lands at here. Some number of times it lands here, and so on. And the first question is, what is the size, typical size of this distribution, right? So okay, so there we ask this question: what is the typical size of this cloud, right? And so let's see how to calculate this object first. So after time n, what is xn square? Okay, so this is very simple to calculate. So xn, so if you use this, if you just iterate it, so in the next time step it's just xn minus 1 plus n. I just wrote xn as this object, and if you keep doing this, it's clear that this object is let's say right. This is clear, I guess. Okay, so now I want to, so this is sum of some n random numbers, each drawn from this distribution. So what is x square? So therefore xn square okay, now I can, so this is a double sum. I will write it as right. Okay, so now I have to just calculate these objects. Okay, so so what is this zeta L square average? It's okay. So zeta L is a random number which is 1 with probability half. So therefore zeta L square average, each step it's an independent random, and this is a distribution. So it's 1 with probability half, and -1 square is again 1. So 1 with probability half. So this is equal to 1, right? So zeta L square average is just 1, and so all of them will just give 1 1 1 1. So you have n, right? So this is equal to n, and this object is these two guys are independent random numbers, and their average is 0, right? So zeta L average is so it's 1 with probability half, and -1 with probability half. So therefore this is 0, right? So this term doesn't contribute, and so you get xn square average is basically n. Okay, so it's let's see if you can quickly do this calculation for this this case. Okay, so that's actually very easy to generalize to the two-dimensional case. So in this case, I have a right. At each time. Okay, so here let's say the space is continuous, and but time is, let's say, still discrete. Okay, so at each time step the mosquito goes random distance, it goes a fixed length step a in a random direction, right? So what should I write for this guy? Okay, so let me just make it clear. It's here. So the walker is in this two-dimensional plane x y. It starts from some at time step n, it's at some point. At the next time step it chooses a random vector, right, and just moves in that direction. Okay, so so it could be any vector chosen randomly. Okay, so what how should I write this? E to the power I theta, right? But if it's that's a complex, but I just want to write x and y. Okay, so that's okay. So it's basically it's a vector which looks like A is the distance, right? And then what? Right. And basically, I mean, if I this zeta n is a, I said it's a random vector on this line. So theta, if I just choose this angle randomly between 0 to 2 pi, then I generate a random vector on this circle, right? So I just need to parameterize this by this angle theta n, and that will generate a random number on this here. Okay, so theta n is uniformly okay, so this is a continuous variable, okay, and so it's chosen from a probability distribution. Okay, so this is for each step, and now you can see that it's very easy to repeat this calculation, okay, and each of these zeta n is still independent, okay, and we just need to what you will see is you just need to find its mean and variance, okay, and then you can just calculate this this size r square. So we repeat the thing which we did in the previous thing. So it's now so n steps, and in each step I have zeta n bar. So it's a sum of random vectors, and now if I take x n bar square average, okay, so this is now what? Right. So again I have to look at the variable. So this is my zeta n bar. So if I take square, what is it? Huh? Square is just a square, right? Because cos square theta n plus sin square theta n is 1. So it's just a square. So this is therefore just equal to n a square, and this. So these are again these are independent random numbers. So I can write it as zeta L bar right. If they are independent, I can always do this. Now what is this average? So this is my vector, right? So what is the average of this guy? 0, right? So average means basically so what is cos theta average? So this is by so theta is a random number from a distribution, uniform distribution between so this is basically this is p of theta 1 by 2 pi and cos theta. So this obviously is 0, right? So and that's obvious and physically, because each time you go in a random direction, so average must be 0. So this is 0. So it's just n a square. Okay, so okay, so in 1D random walker we saw that x n square is equal to n for so this is on discrete random walk on a 1D lattice, and then for a 2-dimensional vector we saw x n bar square is equal to n a square. Okay, so this is a it's still on the continuum but in discrete time, and sorry, so I should call this n. So in n time steps it moves this much. Okay. So now this is actually one of the most important things about diffusion process, that the size of the process grows as root of n, root of time. Okay. So if you imagine that okay, so
In the first case, it is n because you put the time stable length to be
1.
It should be n square.
Yeah, because I was doing on a lattice with a equal to 1. Okay, I mean you can just put a lattice space. If you, this is right now, this has no dimension, right? It's a lattice size is 1. If you put a lattice size, it will be a square, so it will be the same. But okay, so what I am trying to say is that the important thing is that it's proportional to n, the number of time steps. Okay, so if you typically, if you like, I mean, if you are, if things are let's say determined by a deterministic model, where then things are typically ballistic. Okay, so if you moving with constant velocity, then after time t you move v into t distance, and x square would be t square, right? But here, because you are doing this way, so you move much less. Okay, so you I mean if you so typically if you look at how x goes with time, so x means here x average is of course 0, right? In both cases x in average is 0. So the average is 0, but the typical distance, which is like you might just think of something like xn mod, let's say. How does this grow with time? That grows as so let's say xn mod, it grows as root t. Okay, so if it was linear, if it's ballistic, it grows like this with time. So this is what you would call ballistic motion. Okay, and if it's diffusive, then it's kind of much slower. So root t means it goes like this. Okay, so it's a very slow process. And then of course you can have things like there are processes where you can get instead of, so this is x square equals to 2 dt. Okay, so usually you write it as time times some constant which you call the diffusion constant, and okay, so the important thing, x square goes as t. If it is ballistic, it's t square, so that's called ballistic. And then you come across various other systems where actually it might be some t to the power some power, different power nu, and nu could be either less than 1, so those are called subdiffusive systems, or it would be greater than 1 but less than 2, which are called super diffusive. Okay, so I mean, so all these things again you can understand by generalizing this random walk model, which we won't do, but it's just good to know. So nu less than 1 is called, so these are really slow processes. Okay, this happens in systems like glasses and all, where things really can't are stuck. Okay, so they just can't move, so it's very slow. And then in some systems you find that nu is less than 2 but greater than 1. Okay, so these are called like super diffusive. Okay, so but basically what I am trying to say is that this is one of the most important signatures of a diffusive process, that the size of this cloud grows with time as root of t. Okay, so if you are, I mean, so you are interested in how far these mosquitoes are spreading. They are, if they are doing a random thing, then they are spreading quite slowly. Okay, I mean, if it was t, it would have been much faster. But so at large times, I mean, this one is much slower than this. Okay, so it's a very slow process, diffusion. So that's why if you put, yeah. Okay. Shorter times, okay. Okay, shorter time. Okay, this of course finally depends on where you put the velocity and time scales, and but really short times, of course, if it's really diffusive, it will always be faster than yeah. But if you look at like let's say Brownian particle and all, then at really short time scales, actually it's not diffusive. Okay, it's actually ballistic. Okay, so so there's a crossover from ballistic to diffusive. I don't know about, yeah, probably that's true of mosquitoes also, right? Because if you look at a very small time, I mean, before it realizes that it's actually doing a thing. I mean, if you are just looking at this time scale, then you will just see t square. Okay, so at really short time scales, typically I think you will just see this the ballistic thing, okay, and then it goes to at long times it's diffusive.
Why is that?
Sorry,
Why does it behave
like what?
at short times?
At short, okay. So for if you look at like okay, what is a good way to understand? Okay, so right, yeah. This of course depends. I mean, you have to make them dimensionless and all, right? Otherwise, it doesn't make sense to talk of 0 to. I mean, in what dimensions are? So you have to make everything dimensionless. Then you can talk of 0 to 1 and so on. So right now, this is not very representative. You can't just say 1, right? Because 1 doesn't mean anything. It depends on how you choose time and so on, in what units. So you have to. So I mean, it's so here it doesn't make sense. But what she's asking is, I'm saying if you take a real colloidal particle, then at short times actually you won't see this this diffusive behavior. It really goes ballistically. And okay, what is a simple simple explanation is, okay, I mean, one way to see it is because I mean the reason is diffusive is because of this random collisions. Okay, so there's some time scale for these collisions to really take, I mean, to show up. So before that time scale, I mean, you just move ballistically. Right, yeah.
See, if I have an isolated container, put some water and take a pollen grain,
Yeah.
and it's really isolated, there is no external light.
Right, yeah.
Then also will it be, I mean, there is only this molecular motion, microscopic.
Right, yeah, no, that's what I'm saying is, okay, so you have this pollen grain, right? Not pollen grain, okay, so some colloidal particle, and you have this lots of these small particles, right? And it moves randomly because of these random collisions from these guys, right? But this collision, there's sometimes collisional time scale, right? Before that time scale, I mean, it will just move completely deterministically. Okay, so at a really short time scale, it doesn't see the random effect. Okay, so if you really started, for example, even if you write what's known as the Langevin equation, I think you will talk about it, right? So if you really start with the Langevin equation and then calculate this mean square, this x square quantity from the Langevin equation, you will find that at short time scales it's actually ballistic. Okay, yeah.
But that short time scale is just one step, right? Because I mean, when I'm taking one step in the random walk, that is when it's like ballistic.
No, in this random walk picture, it's diffusive at all times. That because I have already.
I mean, even when you look at the mosquito.
Right, yeah, there is a diffusive at all times, but if you go at a more microscopic level, right, if you really write the full equations for this colloidal particle, for example, which has the effect of the noise and also of the bath and also the its own independent, like Hamiltonian dynamics, there if you look at short time, so there of course it's not exactly n at all times. Okay, so there you have more complicated formula, which will look which will be diffusive at long times, but at short times you will find that it actually goes as t square.
The mosquito case, if you just associate a time scale which takes to take that state portion, he's saying the time scale is 1, but if you just really put the time there, the mosquito is just going with some velocity v, right?
Right, yeah.
If you look at the time scale less than that, then it's like a mosquito is moving with a random velocity in one direction. So x is just vt, where v is random. So x square will go like t square.
T square, right, yeah.
With some t square average, right? So that's the time scale.
Right, yeah. Okay, so yeah. Sorry. Okay, example of subdiffuse system is I think okay, like even in this what is popular is if you look inside a cell and look at diffusion of various objects, because there is a very messy thing, right? There's all these things called cytoskeleton and some very complicated structure inside. So things keep getting trapped. Okay, so and one popular model is like there's a, you take a step and then you wait for some time, okay, because you are trapped, okay, and then again you take another step. So it's just an extension of this model. Okay, so here I am saying at each time step I do something, but you could also write a model where at each time you move, then you are trapped for some time, and this time is chosen from some distribution. Okay, so there is a distribution of waiting times, and then again you move randomly. Okay. So, for such a model, if you calculate what is this mean square displacement, then you will find it's goes subdiffusive. Okay. That also depends on this waiting time distribution, because basically the idea is that you are trapped in some region for a long time. Okay. So, there is a waiting time distribution which has long tails, and then you move finally you move very slowly. So, that is the basic idea.
Super diffusive.
Yeah.
So you choose this random variable, so in 1D for example, so if you choose like moving to right and moving to left with different probabilities,
With different probabilities.
then you will get super diffusive.
No, if you okay, I'll just do that. Okay, so let's just do that example. You're just saying different probabilities left and right,
Yeah.
right? Okay, so let's just do that example since this. Okay, so and then we'll come to probability distributions. So just now we are just looking at the variance of the probability. So there's a distribution of this position of the mosquitoes. We are right now just looking at the variance, right? And okay, so let's just look at another model. Okay, so what he is talking about is called the biased random walker. Okay, so it's still given by this xn n, and okay, so let's make it slightly okay. Where p minus 1 with probability q, and let's make it even slightly more complicated, just to show that you can do things quite. You can make it slightly more complicated, and the calculation is still simple. Okay, so let's also say that there is some probability that you don't do anything. Okay, so it stays 0 with probability 1 minus p plus q. Okay, so p plus q of course has to be less than or equal to 1. If it is equal to 1, then it's there is no weighting probability, otherwise there is also a weighting probability. Okay, right. So I mean, is this the model you are thinking of?
Yeah.
Right. Okay. So now what is let's do this calculation again. So again it's clear that xn is equal to sum over n. So this is still true, and square it and break it up into L equal to m and L not equal to m. So that's still true. Okay, and they are independent. Each step is independent, so I can still break this up into xi L average and xi m average. Okay. So now, okay, so first of all, let's calculate this object and these two things. Okay, so what is this xi L square average? Okay, what is it? Huh? P, okay, so 1 with probability p and 1 with probability q and 0 with probability whatever. So this is p plus q, and what is xi L average? It's 1 with probability p and minus 1 with probability q and 0, so it doesn't matter, is equal to p minus q, right? Okay, so so this is not 0 now, right? Earlier it was 0, now it's not 0. So therefore this object is then n times p plus q, and how many terms are there? So I mean, originally there were n square terms. I took away n terms, right? So therefore this one has n square minus n terms, which are all equal, right? Because each of them are identically distributed. Okay, so right. So this is xn square, but you should also calculate xn average. Okay. So xn average is not 0 in this case. So xn average is what? Xn average is just average of this, and so that's just n times p minus q, right? Okay. So now I mean, so now what's happening is I mean, if you I mean, initially the walker started from here, but now it's more there's a high, let's say p is greater than q, then it's more, with more probability it's moving in this direction, right? So at some time n, you will find that I mean, most of the particles, the mean is at this point, right? So if you look at the distribution, you will find that so this is p of x at time n. You will find that the mean of this distribution is located at this point, right? N times p. So this is okay. So is located at some value like this, and so it's okay. So afterwards we'll show it's the form of this distribution, but basically the mean is now somewhere here. Right, and there's so now what you're interested in the variance. Okay, so of course if you just ask how does x square grow, that grows as n square, right? For large n you can neglect this term and you can neglect 1, so it's basically n square. Okay, so x square of course just goes as t square, so it's because there's a drift, I mean there's a constant velocity, so it moves like that. Okay, but what you should really look at this diffusive thing is the variance of this cloud. Right, so okay, what is a good example? I don't know. Okay, so if you have like if you take a beaker of water and if you put a little bit of let's say ink at the top, okay, so then there's the whole cloud will move down, right, because of because there's a drift, but drift is because of gravity, right. So the whole thing will move down with some velocity, and that's just the terminal whatever terminal velocity of this blob, and then it also spreads. Okay, so that's the diffusion. Okay, so you really need to calculate the variance of this object. Okay, so you should look at xn square, and so this is called a cumulant. Okay, and so if you do this, something goes. So this is equal to if you square it and subtract this minus this, so then this n square I guess goes away, right? So you are just left with q and minus square. Okay, so this is n. Okay, I don't know, p minus. Okay, so anyway, this is the. Is there a simpler way to write this? Okay, no, right now no, because if it was if q was 1 minus p, then it would be easy. But otherwise, you just keep it like this, whatever it is. So now again, you see that the spreading of this cloud, that is Gaussian, that is diffusive still, right? So so the whole cloud is moving ballistically with some velocity v, and the velocity is just actually p minus q. Okay, and but it's spreading diffusively. Okay, so it's still time t. Okay.
So how is this waiting probability getting manifested in this model?
How is that?
Waiting probability that
Oh, it only thing it does is if you look at this object and so finally there's a diffusion constant, right? So if p plus q is 1, which means there's no waiting probability, then you get a larger diffusion constant. So just the diffusion constant just becomes smaller. Okay, but because this is a simple waiting probability, it won't give you like it won't give you subdiffusive or anything. Okay, so for that you need more complicated waiting time distributions. So this will just give you yes. So it just changes the diffusion constant. So I think you can show that this quantity is largest if p plus q is 1. Difference between line number 3 and oh, this one. Here I okay. So I am looking at this. Here I am looking at this minus square of this. Right, here is just the moment, and then I am taking the moment and subtracting the mean square. So that's really the standard deviation, right? So this is called usually a cumulant. Okay, so cumulants are so this is called a moment, and this is called a cumulant.
People also study super ballistic models.
Super okay, so super ballistic. Okay. Okay, I don't know. Is there? In principle, one can, but I don't know of an example where.
Accelerating.
Maybe let's write an dn x dp and.
Yeah, I mean it's easy to find a system where but I don't know of a physical example where you have. Yeah, if you have an accelerating system, of course it is okay, in some sense, but it's kind of trivial. Okay, so right. Okay, so that's about the variance of the distribution. Now let's try to compute the actual distribution. Okay, so basically the point is that after n steps, so let's go back to this 1D walker. So it can be anywhere in this range, right? The maximum it can go is if it just keeps going on to the left, it can go minus n, or if it goes to the right, it can go n. Okay. So it can be at if I do an experiment many times, I will land up at various places. Now I ask what is the probability that I am at x. Okay. So p of x n. Okay, so here you should remember that this is discrete. It can take values minus infinity to infinity, but integers, and this is also discrete. Right. And this is actually a probability. It's not a probability density, right? It's just a number between 0 to 1 in this case. A discrete random walk. Okay, so now I go back to my this unbiased random walker model. So P is equal to Q is equal to half. Okay. So we'll talk about this case. So this all of you have done, and the usual trick is to so how to find this probability. So basically you take n steps, right? And so out of these n steps, I mean some number are on the right. You take right steps, and some steps are left steps, right? So I mean so typical walk is like right, left, left, okay, left, right, and so on. Okay. So this is the random walker. First step he goes to the right. Next step he goes back left. Next step left, left, and then again right, right. Okay. So this is a typical walk you will do 1, 2, 3, 4, 5, 6 step random walk. Okay. And after 6 steps you land up at in this case you land up where you started from, right? So you land up in the origin. So in general you will land up at some point x, and so what you can say is clearly L plus R. Okay, so So total number of steps must be n, and I am saying that after after n steps I am at okay. So this is again small n, right? Yeah. And so r minus l is equal to x. Okay, so x is my final position, and clearly r minus l must be x. Okay, so now therefore, I mean if I know n and x, it completely determines r and l. Okay, so therefore r is x by 2. Okay, now this r and l steps, I mean of course they are not all r and l, I mean I can mix this r's and l. So this is like r, l, 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 r, r, but another realization with the same number of r's and l's is r, 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 l, 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 right. So this would still give me the same value of n and x. Okay, so then I have to ask how many ways can I get n and x, and that clearly is n factorial by r factorial in l factorial. So that is number of ways I can get a given value of n and x. Okay, and the probability of each of these is basically what, 1 by 2 to the power n, right. Therefore this is really the probability that I am at x at time n, right. I hope this is clear. And then so basically you put the values of r and l, and so okay, so this basically gives you the probability distribution. Okay, so one thing you should notice is that if right, this is clear, right. After one step you can only be in odd place, after two steps you can only be in an even place, right. Okay, so if you plot this function, let us say, I mean, so okay, so let us take n equal to 4. So okay, so 4 means there are 16 possible steps, steps, and if you calculate this object, let us say what is p of 0, 4. So that is 4 factorial divided by 2 factorial, 2 factorial, and 1 by 2 to the power 4. So that is 6 by 16, right. Okay, so yeah, so 6 by 16. So then you can calculate what is p of let us say 2. So p of 1 4 would be is what? P of 1 4 is 0, right, because in you can of course if you put it in this formula you will get some funny thing, but it's basically it's 0, right. You will get some fractional factorial, but you know it's 0. Okay, so p 1 4 is 0 and p minus 1 4. Then you can ask what is p of 2 4. So that's basically 2 factorial, no sorry, 4 factorial divided by so you put 2 here, so that's 3 factorial, 1 factorial, and 1 by 2 to the power 4. So that's 1 by 4. Okay, so okay, so let's calculate p of 4 4. So what is it? 4 4 is 1 by, there's only one way you can go, right, to the end. So that's just 1 by 16. Okay, so now you can plot this on this graph. What is the probability of finding it at various places after 4 steps? So this is 0, 1, 2, 3, 4. Okay, so at 0 I have some number which is 6 by 16. So let's call, so this is something here. At 1 it's 0, at 2 it's basically 4 by 16, so it's slightly less than this. So that's let's say somewhere here. Here it's again 0, and here it's 1 by 16, right? So somewhere here, and then it's all 0. So the distribution is basically looks like this. I mean, -4. So there are you have just these 5 numbers which have known. So you can bet 5 different places, and those are the probabilities of being there. Okay, so now let's do something. So we'll try to look at this formula when this n is kind of large. Okay, so if n is large, then there's something called this Stirling's approximation. Okay, so there's something called Stirling's formula. STIR or ER? I. Stirling's. Which says that n factorial is equal to n to the power n Okay, so this is a very nice and useful formula which I think many of you have used. It's also actually nice to derive this formula. Okay, so so do you people know how to derive this formula? Huh? Has anyone derived ever derived this? So, okay, some people maybe have, but there's a very nice and trick to derive this. Okay, so maybe I'll just tell you about. So this is n factorial. You can write it as 0 to infinity what is it, 0 minus x, right, minus x x to the power n, right. This formula everyone knows, right. Then you can do a very simple trick. Okay, so what you can do is you can write this as you want. What you want to know is the form of this for large n, right. So what you can do is you can rewrite this as so this is still the same. Okay, and then I write this as I put these two together. So this gives me n, right. Okay, so basically I want to evaluate this thing for large n. Okay, so then there's a trick, it's called the saddle point method, where you look at this object and you find where is it. So if you plot this thing, it has some maximum somewhere. Okay, and for large n, it will the most contribution will come from the maximum where it's maximum. Okay, so this function, and what I'm saying is it looks like it has a maxima at some place. Okay, I don't know where it is. Okay, so wherever it is. And for large n, this integral gets the maximum contribution from this region. Okay, so then you can just expand this function around the maximum. So first you have to find the maxima. Okay, then expand this around the maximum and do a Gaussian integral. Okay, and that will actually just give you this result. Okay, so this is a good exercise which maybe you can do. It just teaches you this thing called the saddle point method. Okay, which is very powerful and used quite often in physics. Okay, so anyway, we use this saddle point formula to replace n factorial by this stuff, n to the power n into the minus n and root 2 pi n. So, so if you do this then at the end of the day what you will get is okay. So okay, so another thing that I should say is that even though this is an large and approximation, okay, so I should say, so you should always write approximately. So even though this is an approximate formula, it's actually already very good, I think, at like n equal to 6 or something. The difference between this and this will be maybe, I don't know what, 5 to 2% or something. Okay, so it's already very good at n equal to 6. Okay, so you don't, large n doesn't mean like 10,000 or something. Okay, so if you do this Stirling's approximation and then just use this here in this one, and do some simplifications, the final formula you get is P of x n is equal to what is that? Okay. Okay, so this is what you will get. Okay, so okay, so this is I have just used this this formula and use no other approximation. Okay, so this is still exact and it's still a probability. Okay, it's not a probability density; it's still a probability. Okay, so now what you can, so now you can see that it looks like a Gaussian distribution, and many of you know that. Okay, this is okay. So maybe I should declare small n and capital N are equal. Okay, so okay, so this is the expression, and now okay, so now what we want to do is find the distribution. Okay, like now imagine that actually there's this lattice, there's some size A. Okay, and I am looking at a course, like I am doing some coarse graining. And so I can't really see these lattice sizes. What I can see is I can in some region dx, okay, I can I want to know how many, what is the probability of the particle being in some region dx, okay, and dx can contain many of these cells. Okay, I mean okay, so then what I should do, so I want to now calculate a probability density, right? What is the probability that the particle is from x to x plus dx? Okay, so now I will change variables. I will use a continuous variable x which has dimensions and is like x times a. Okay, and okay, and also let's imagine that each time step takes some time tau. So I will introduce time which has dimensions and is n times tau. Okay, so this is each time steps takes some time tau, and this is the lattice size. Okay, so this is now a kind of continuous variable, and this is also, and I want to find p of x t dx. So now I want to find this p of x t density, which gives me the probability of finding between x to x plus dx. Okay, so this is now a probability density. And this is a probability. Okay, so now what I have to do clearly is that in some region dx, I have to sum up all the probabilities. That's the total probability of finding a particle in this small dx, and then divide by the length dx, right? Okay, so now what you observe is that so what is the minimum value of dx I can take? Okay, so in this problem, see what I said is that at 2 it's some value, but at the next time step it's completely 0, right? It's a highly discontinuous distribution. Okay, so therefore I have to if I want to get a continuous function, I have to take at least the lattice size 2a, right? So I have to average at least over this point and this point, right? So I have to sum these two probabilities and divide by 2a. Okay, so therefore dx should be at least 2a, and then I just have one probability at that site. Okay, so choose n. Okay, so and so I can of course instead of 2a I could have taken 4a, but then I would have to sum two different probabilities, okay, at a and 2 like at 2 different, but this is the simplest thing I can do. And if you do this, then basically if you so 2a means here you get equal to what 1 by so you can put the 2a inside, so it becomes 4a square, so that's 2 pi a square n to the power half e to the power minus x square by 2n, and then I just replace x by I use this transformation, okay, so replace x by small x and n by t, so this becomes equal to okay, so p of x t is equal to n is t square. Right, okay, so I have just replaced, I have done x to x and n to t. Okay, now I define okay, so this is sort of very important result. So this is in the continuum limit. If you have a like if you start a particle from a point, this is how the distribution looks at time t. So this is a Gaussian distribution, and so this x square, if you use this distribution to calculate the second moment x square, so this is just by definition d of x square p of x t, then you will find that this is equal to 2 dt. Okay, and yeah, right, yeah,
Then if my number of steps are odd, then I will end up at some odd position.
right, yeah.
Now, I should get the same distribution if I average over all the initial positions.
Initially you are starting from origin anyway, right, always.
I mean, it should be equivalent because say
Oh, you are saying you are starting from either 0 or 1.
all initial positions.
All of you, then of course you have to, so this is the answer if you start from a fixed initial condition. If you start from a different initial condition, like p of x0 is different, then this won't be the answer, right. So I mean, what is this? I mean, this is basically see, so finally what were we getting? So basically we have like so this is the x axis. Now think of the continuum now, right. So this is a continuous line, minus infinity to infinity, and I am just putting a blob of ink here, right. So the distribution initially is a delta function, and then I want to see how this distribution changes, right. So the distribution now at time t, it will so after some time it looks like this, and then it spreads and so on. Okay. So at different times it's slowly spreading. The size is like root of 2 dt. Okay. So but this whatever solution I have got is for an initial condition which is at which is a delta function at t equal to 0. Okay. So if you put in this expression, if you put t equal to 0, you should verify that this is actually a delta function, delta of x. Okay. So p of Okay, so some other properties you can check is Pxt is equal to 1. So it's of course normalized to 1, right? So you can see that dividing by this 2a was important. Okay, if you just divided by a, then what you would have got would not have been normalized. Okay, so I mean, so dividing by this 2a is really crucial. Okay, and so that gives you the properly normalized distribution. Okay, and of course here you can ask. I mean, initially my ink may not have been like that. I mean, I can ask a different question, like supposing I have a box and initially all my ink is like this. Okay, and I want to know how it spreads in time. Okay, so this is the initial distribution. Like I have a box with some partition at half at some position, like half of the box, and I remove the partition. How does this thing spread, right? So it will spread in some way, and how will we find how this thing spreads now? Huh? Yeah, so I mean, given this information, can we, I mean, given this solution, so we know the solution for a delta function initial condition, and then if you have any other initial condition also you can find that, okay, using this, okay. Huh? Yeah, Green's function, right, yeah. So basically, and what you have to do is solve the diffusion equation. So okay, so in the next class I will discuss another way of looking at this problem is by writing a diffusion equation. And then you can see how to understand how this kind of initial distribution will evolve in time and so on. Okay, so okay, so we'll stop here. It's time, right? Yeah, and so maybe at the so I have another lecture tomorrow, and then I'll give a set of problems. Okay, so here also there are many steps which are incomplete, and it's good to really, you should really sit down and work every step. Okay, so even if like this Stirling's approximation and calculating, doing all these steps, I mean, it's really important to work through every small detail and make sure you understand everything. So also we'll give a set of problems on Friday, which is tomorrow, and in the weekend you are supposed to basically solve all those problems and return it on Monday. Right? I mean, very simple problems, but at least it's good to make sure that you know the simplest things really well. Okay. So now there is coffee, and then we start at 11:30.